In this video, we're going to take a look at hydrohalogenations and hydrations of alkynes, and all of these reactions are extremely analogous to their alkene counterparts. For example, we can combine an alkyne with a hydrogen halide HX, and if we use one equivalent of HX, we get a Markovnikov addition of H and X to the alkyne to produce the more substituted alkenyl halide. So we have H connected to the less substituted carbon and X connected to the more substituted carbon if we use one equivalent. If we use two equivalents, well, we get two X's added to the alkyne in a Markovnikov fashion, so that X ends up linked to the more substituted carbon, and we end up with two new H's linked to the less substituted carbon. In the case of a terminal alkyne, this is going to give a methyl group on the end and a geminal or 1,1 dihalide, kind of the opposite of the elimination process that we've seen previously. The mechanism here is a little bit complicated, to be honest, because the reactive intermediate would not be a trigonal carbocation, but an alkenyl or vinylic carbocation like this. So if we draw a perfect analogy to hydrohalogenations rather, of alkenes, we'd expect an alkenyl carbocation like this after proton transfer, followed by nucleophilic attack by X- to produce the alkenyl halide. The experimental evidence suggests a more complicated picture since these alkenyl carbocations are rather unstable. This termolecular mechanism with three molecules involved in the rate-determining step and a single elementary step in the mechanism avoids a alkenyl carbocation, a vinylic carbocation, but requires three molecules to come together. So it's a little bit hand-wavy, but it explains the reaction outcome and trends in rate and things like this good enough for our purposes. I would say for the purpose of Organic Chemistry 1, keeping either of these mechanisms in mind is completely fine. As the slide mentions here, the truth is most likely a mess. There might be a mixture of these two mechanisms occurring together to give the same products in a typical reaction flask. This is Markovnikov hydrohalogenation, producing the more substituted alkenyl halide. If we want the less substituted alkenyl halide, we have to use a radical-based method, employing, for example, HBr with an acyl peroxide, for instance. And this leads to anti-Markovnikov hydrohalogenation. So notice in the products of this reaction, we get a mixture of E and Z, or cis and trans isomers, but bromine is linked to the less substituted carbon of the original alkyne in both cases. And this is explained by a radical mechanism where bromine radical, which is generated under the reaction conditions, adds to the less substituted carbon of the alkyne to produce the more substituted radical. Addition of bromine at the more substituted position would produce a less substituted and therefore less stable radical that is not observed under the reaction conditions. This radical then reacts with another molecule of HBr, or a molecule of HBr, abstracts a hydrogen from it. This generates a new bromine radical, propagating the chain, so to speak, and generates the neutral alkenyl bromide products as a mixture of cis and trans isomers, because this radical exists as a mixture of cis and trans isomers effectively. And so the overall result, though, is anti-Markovnikov hydrohalogenation. Highly useful if we want to install a bromine in particular on the less substituted position of the alkyne. Acid-catalyzed hydrations of alkynes occur with Markovnikov regioselectivity, exactly what we would expect based on prior reactions of alkenes. There's a little quirk to these hydration reactions with acid of alkynes, and that's that we use mercury sulfate, HgSO4, in these reactions along with a Bronsted acid and water. Something like a mercurinium ion is likely under these reaction conditions, where mercury 2+ adds to the alkyne to produce a cyclic ion like this. And this leads ultimately to Markovnikov selectivity, oxygen bonds to the more substituted carbon, as we'll see. If we look at the final products first, we see that there's a new carbon-oxygen bond to the more substituted carbon. So this is a Markovnikov method. What makes it different from hydrations of alkenes, though, is that we don't end up with an alcohol, with an OH group. We end up with a carbonyl group, a CO double bond. We'll explain that here shortly. So mechanistically, again, we form this mercurinium ion. This mercurinium is electrophilic at the 2 carbons in the 3-membered ring. Now there's a double bond there rather than a single bond in, for example, oxymercuration. And so this is even more reactive than those mercurinium ions we've already seen. Water's going to attack the more substituted position because that's got more partial positive charge, more electrophilic. And ultimately, a proton is going to replace the mercury, and we end up with this structure. Now, this structure corresponds to hydration of the alkyne. We've added an OH group at the more substituted position and an H at the less substituted position. And it's known as an enol, since we have an alkene connected to an alcohol, essentially, enol. But the reaction doesn't stop here. The final product is this ketone. The conversion of the enol to the ketone happens very rapidly under these reaction conditions, such that the final product is, if we're dealing with a terminal alkyne, the methyl ketone, the Markovnikov product. And this process is called tautomerization. We're going to talk about it in a little more detail on the next slide. All you need to know for the purposes of predicting products of acid-catalyzed hydrations of alkynes is that this tautomerization is very rapid, such that the carbonyl product is going to be the major product. These isomers that differ in the position of a hydrogen, with the enol having a hydrogen linked to oxygen and the ketone having that hydrogen linked to this carbon, are known as tautomers. And they interconvert via an isomerization process that involves only proton transfers, only the movement of H+, ultimately from this oxygen to this carbon. And so under these acidic conditions, we protonate at this carbon first. This gives a resonance-stabilized carbocation intermediate, oxygen-stabilized carbocation, and deprotonation at the oxygen generates the ketone product. And this favors the ketone side for reasons that we won't get into in too much detail. All I'll point to is the greater stability of a carbon-oxygen double bond relative to the carbon-carbon double bond. So typically, the ketone product is going to be favored here. Tautomers are constitutional isomers, so we should expect a difference in stability here. And for the purposes of Organic Chemistry 1, you're always going to draw the ketone product in these hydrations of alkynes. If we want anti-Markovnikov hydration of an alkyne, we're going to go back to hydroboration-oxidation, which causes hydration in an anti-Markovnikov sense, with OH ending up linked to the less substituted carbon and the new hydrogen to the more substituted carbon of the alkyne. Now, rather than a ketone, we end up with an aldehyde functional group, since oxygen, the new carbonyl group, appears connected to a carbon bearing a hydrogen. One thing I should mention about this reaction and acid-catalyzed hydration is that this regiochemical issue comes up with terminal alkynes, since the internal carbon is going to be linked to an R group, and the one on the end will be linked to a hydrogen. So this is the only type of alkyne that can have a difference in substitution pattern. Internal alkynes, unless they're delightfully symmetric, are going to give a mess of products in both hydroboration and acid-catalyzed hydration conditions. So we care most about this when we're dealing with a terminal alkyne. And when we use hydroboration on a terminal alkyne, we end up with an aldehyde after the oxidation step. Now, hydroboration-oxidation leads initially to an enol, analogously to the acid-catalyzed hydration case. We just add H and OH across the carbon-carbon pi bond, essentially. But tautomerization occurs here again, now under basic conditions, promoted by the NaOH rather than acidic conditions. And it's still proton transfers, and the net result is still the movement of a proton from here to here. So first we have deprotonation by the base. This generates what's called an enolate anion. A resonance-stabilized carbanion is one way you can think about this. That carbanion is then protonated at carbon to generate this aldehyde product, and the aldehyde structure is more stable than the constitutionally isomeric enol. So the final product you should draw is the aldehyde rather than the enol form. In summary here, if you want to do Markovnikov type hydration of a terminal alkyne, we're going to use acid-catalyzed conditions with a Bronsted acid, water, and mercury 2 sulfate, which acts as a Lewis acid. It's necessary for this reaction as well. If you want to do anti-Markovnikov hydration, generate an aldehyde from a terminal alkyne, we use hydroboration-oxidation, BH3THF in the first step, and something like sodium hydroxide and hydrogen peroxide in the second.